We finally introduce the data structure, the heap, that is used to implement the abstract data type priority queue. A heap is a complete binary tree except for possibly the bottom level, which must be filled from left to right. All nodes in a heap must be comparable. In addition, the following property must be fulfilled. Each node must be less than its children. This property is called the heap property. The kind of heap we consider is called a min heap because the root must be the smallest node due to the heap property. If you read up about heaps in different textbooks, some might define a heap as a max heap where the root is the largest element. The heap property for max heaps requires that each node is greater than its children. Here we only consider min heaps. So if we talk about the heap property, we refer to the property for min heaps where each node is less than its children. Let's look at an example heap. This heap has 6 nodes. Since a heap is a complete binary tree, except for possibly the bottom level that is filled from left to right, all heaps with 6 nodes will have the exact same tree structure. There's one root node with 2 children. The left child of the root has 2 children itself, and the right child of the root has 1 left child. Now we could use a linked structure to store a heap in memory, just as we did with binary trees, for example, but instead we will store the nodes of a heap in an array where the nodes are placed in the array in level order. In the given heap, the level order of the nodes is 1, 3, 5, 6, 7, 9. So the tree is stored as an array with the elements 1, 3, 5, 6, 7, 9 in that order. Now have a closer look at the array. Interestingly, the array is sorted in this particular case. It makes sense that the first element in the array is the smallest element, since the root is the smallest element in the heap and must be the first element in the array. But is every heap represented by a sorted array? The answer is no. Look at another heap. This heap contains the same elements, but they are differently arranged. Now the level order of the nodes is 1, 5, 3, 7, 6, 9. Since a 3 comes after the 5 in level order, the resulting array representing the heap is not sorted. In other words, the array that represents a heap may or may not be sorted. Okay, then let's look at another question. Does any array, no matter how its elements are arranged, represent a heap? You can imagine this is not the case. I am using again the same numbers as before, but now arranged differently in an array. The binary tree that stores these elements in that order, in level order, is as follows. Note that the node 7 is greater than its right child 5, and therefore the tree is not a heap. I have one more question for you. Let's say you have a sorted array. Does every sorted array represent a heap? Actually, it does. It is not very hard to see. Assume you fill a complete or almost complete binary tree with the elements of a sorted array in level order. Now take any node and its children. That node will come before its children in level order. So it comes also before its children in the sorted array, and therefore that node must be less than its children. If you got all that so far, you have a pretty good feeling for a heap and its properties. So let's move on to the implementation details. Okay, we said we store the nodes of a heap in level order in an array. Now in many operations on a heap, we need to access a parent or the child of a node. Interestingly, this works out great using an array. If you have the index in the array for a node, then you can actually calculate the index of its parent and its left and right child. So the left child of a node at index I is located at index 2i plus 1, and the right child of the node at index I is located at index 2i plus 2. The parent of the node at index I is located at I minus 1 over 2, where we round down in case there's a fractional part. Now we are ready to look at the heap operations. The operations correspond exactly to the operations on a priority queue. We can add an element, get the minimum element, and remove the minimum element. So if you want to use a heap to implement a priority queue, then you would use the priorities of the items to compare them. And the items would be sorted such that the higher the priority, the smaller the item. In other words, the item with the highest priority would be the smallest item in the heap. We go through the operations one by one. The add operation has to make sure that when adding the element, the binary tree is still complete, except for possibly the bottom level, and that the heap property is met. We first demonstrate how the add operation works in a small example heap. Let's say we insert 5 into the heap. We first add 5 at the bottom level, so that the bottom level is still filled from left to right. As an aside, that is easy to do in an array because that means the new node is added to the right of the last element in the array. Of course, now the heap property is in general violated. It can happen that the new node, like in this example, is less than its parent. So what we do is we swap 5 with its parent 11. Now 5 has a different parent and might still be less than its new parent node. As in the given case, 5 is less than its parent 9. So we again swap 5 with 9. Now 5 has a parent 2, which is less than 5, and the tree is a valid heap. In summary, we add the new element at the end of the heap first. Then we restore the heap property if it is violated as follows. We compare the new element with its parent. If it is less than its parent, then the heap property is violated and the element is swapped with its parent. If it is greater than its parent, the tree is a valid heap and the add operation is done. If the element has been swapped with its parent, we have to continue comparing the element with its new parent and possibly swapping until it has reached a position where it is finally greater than its parent, or it has reached the root position and thus doesn't have any parent anymore. The get minimum operation is the simplest operation. Remember that the smallest element is the root, so the get minimum operation just returns the root. If the heap is stored in an array, then we know the root is the element at index 0. Finally, we get to the remove operation. We want to remove the minimum element. As we know, the minimum is the root, so we can directly access the element to be removed. But we can't just take it out and leave the tree without a root node. So first, we restore the tree to be a valid, almost complete tree by placing the rightmost leaf at the bottom level in the root position. Now the heap property might be violated, as the new root might be greater than its children. Indeed, this is the case in our example, so we need to restore the heap property. In order to do so, we compare the new root node, in our case 11, with its smallest child, which is 3 here. Since 3 is less than 11, the two nodes are swapped. Note that it will not help if we swap 11 with 5, because then there is still the problem that 5 is greater than the other child, 3. 11 is in a new position now and might have to be swapped further with its smallest child until 11 is at a position where it is less than its children, or when 11 becomes a leaf node. In our example, 11 is indeed greater than its smallest child 4, so 4 and 11 are swapped. Now the heap property has been restored. In summary, the remove operation replaces the root node by its rightmost leaf at the bottom level. Let's call that leaf E. Then the new root E possibly needs to be swapped several times with its smallest child. That operation is done in the method heapify. So heapify E compares E with its smallest child. If that child is smaller than E, then the two nodes are swapped. The process continues until E becomes a leaf node or until E is less than both of its children.